A particle starts from rest with acceleration 2 plus 6t meters per second per second. That's its acceleration at time t, and after 2 seconds the acceleration changes to the constant value of 14 and is then maintained at this value. Find the distance covered in the first 5 seconds of the motion. Well, those first few words are quite important. It starts from rest. So when t is nothing, v is nothing. It starts, i.e. when t is nothing, at rest, so v is nothing. That's going to come in very useful later. When you differentiate displacement, you get velocity. Integrate velocity, you get displacement. Differentiate velocity, you get acceleration. Integrate acceleration, you get velocity. This question, we are given the acceleration, 2 plus 6t. You can see it's not constant. As t changes, a changes. So we cannot use the SUVATs. We must use calculus. But that, however, is only for the first 2 seconds. So after the first 2 seconds, acceleration does become constant. So then we could use a SUVAT equation after that. Let's integrate this to get velocity, not forgetting our constant of integration. Subbing in what we wrote down earlier, when t is nothing, v is nothing, tells us that c1 is actually 0. So now we know the velocity for the first 2 seconds can be given by this formula, but that's only valid for the first 2 seconds. Now let's integrate that to get displacement, which I've called s, another constant of integration, and let's find it. Well, it's starting from rest, and then we are finding the distance covered in the first 5 seconds of motion. So we just want to know how far has it traveled in these 5 seconds. So it makes sense to say, okay then, when t is nothing, it hasn't traveled anywhere. It's at the beginning. So we can say s is 0 when t is 0 if we want to. In fact, we could probably choose any number we want here, but it's simplest to choose 0. If we didn't choose 0, we'd make it more complicated for ourselves. So subbing those in, we get c2 also turns out to be 0. So now we know for the first 2 seconds, the displacement is t squared plus t cubed, but only for the first 2 seconds. So let's find how far has it moved in the first 2 seconds. If we let t equal 2 in that little formula, we get 2 squared plus 2 cubed, so 12 meters. It's 12 meters from the start after 2 seconds. We need to think, has this particle changed direction? So did it start moving forward, stop, turn around and start moving backwards? Because then for the distance, we'd need to know how far has it traveled forward, how far has it traveled backwards. If we look at v, or we can look at this version, v can only be positive. It's 0 when t is 0, but then as soon as t becomes positive, v has to be positive as well. So that means it's always traveling in one direction. We don't need to consider how far it's gone forwards, how far it's gone backwards. I'm now going to work out when t is 2 and its acceleration changes to be constant, how fast is it moving? So using this formula up here, when t is 2, the velocity is 2 times 2 plus 3 times 2 squared is 16 meters per second. The reason I'm doing that is because now the acceleration changes to be constant. So now we can use a SUVAT, and that is what I'm going to do next. So when t is 2 seconds, it's traveling with a speed of 16 meters per second. So that is our u. So that's not the initial velocity of the whole journey. It's the initial velocity for the section of the journey when the acceleration is constant. So the initial velocity is 16, that's why I worked that out. Acceleration, we're told, is 14. This next bit of the journey doesn't last for 5 seconds. It only lasts for 3 seconds. So t is 3. T is how long the journey lasts for. Subbing those into s equals ut plus half at squared, we get 111 meters. So that's how far it travels between t is 2 and t is 5. So to answer the question, the distance covered in the first 5 seconds of the motion is going to be the sum of these two distances, the 12 meters plus the 111 meters. So the distance covered is 123 meters altogether.